Assalamualaikum and good day. My name is Farhana Arissa and I'm from Malaysia, Japan International Institute of Technology, University Technology Malaysia. As for today, I will be presenting our work on the post-cutting surface evaluation of the copper foil substrate grown with single-layer graphene. First, I will start with the introduction. In experimental work requires repetitive experiment using CVD graphene on copper foil. Purchase of many small size sample can be expensive. This can be overcome by purchase of one large size sample and cut into small size. It can be cost effective. The cost below shows major difference in terms of the price. One piece of 2 x 2 inch graphene costs around $215 and it can be cut into 4 small pieces with size 1 x 1 inch. When the cost was divided, one piece of cut CVD graphene on copper foil only costs $53.75. This is way cheaper if compared to buying 4 pieces of 1 x 1 inch CVD graphene on copper foil separately. However, it is important to note that the cutting process might change the substrate surface and edges properties, especially at the cut area. Therefore, microscopy analysis is important for surface evaluation on copper foil substrate grown with single-layer graphene prior to further experimental work. Microscope is an instrument used to observe larger and more detailed images of samples that the human eyes cannot see. Microscopy analysis is important in this study to evaluate the surface quality and edges condition of the cut copper foil substrate prior to future work in the synthesis of graphene nanocomposite for nanofluid application. 3 types of microscope were used in this study, that is light microscope, laser microscope, and electron microscope. This is because each type of microscope has different wavelength and different image resolution. For experimental work, copper foil substrate grown with single-layer graphene in original size of 2 x 2 inch was cut into small size sample by using a pair of high-quality stainless steel scissors. Fine-tip stainless steel tweezer was used as a handling tool. For microscopy analysis, observation was performed on the same cut substrate in following order, that is, optical microscope and digital microscope, 3D laser scanning microscope, and field emission scanning electron microscope. Each type of microscope has different illumination sources. Figure 2 shows the image of the front side surface taken by digital microscope and image of rear side surface taken by optical microscope. From the results, the line texture of the copper foil substrate can be observed in both the images, although that with optical microscope was not clear due to different magnification. Other than that, line texture was not clear in optical microscope due to depth of field becoming shallower as the magnification increased while zooming. Additionally, the single-layer graphene on copper foil substrate could not be observed since its optical density is about 2.5%. VSEM was then performed at high magnification on both sides of the copper foil substrate, which then confirmed the line texture of the copper foil substrate. Further analysis with 3D laser scanning microscope shows that wrinkles could also be observed on the cut substrate as shown in figure 4. Non-uniformity of the surface can be observed in the areas where the wrinkles emerge, mostly close to the edge of the substrate. This non-uniformity can be considered to be caused by uneven surface contact and force distribution during the cutting and handling processes by using scissors and tweezer respectively. However, the wrinkle that emerged at this stage did not affect the presence of the grown graphene layer on the foil substrate. Next result is the edges condition of the cut sample. Figure 5 is the VSEM images of the cut edge area. VSEM result shows that the cut area exhibited local surface deformation and creases near the cut edge, which then caused the edge roughness on the cutting surface. The cutting process involves friction between the scissor and the copper foil substrate. This friction has developed edge roughness during the cutting process was attributed to the existence of cutting force. Although cutting the substrate using a pair of scissors produces edge roughness, this method is still recommended compared with cutting the substrate using a diamond cutter or knife. This is because this method can prevent damage to the graphene layer as it avoided direct contact with the substrate surface. The roughness, however, can be reduced by controlling the speed and the angle of the cutting forces. As a conclusion, in this study, CVD graphene on copper foil was cut using a pair of high-quality stainless steel scissors. A large-size CVD graphene that cut into small pieces for use in various experiments may reduce the research costs. Surface observation analysis of the cut sample uses 3 microscopes with different illumination sources to evaluate its quality before being used for the next experimental study. In the post-cut substrate, wrinkle at the substrate surface, surface roughness, and edge roughness at the cut area were observed, which attributed to the uneven surface contact and force distribution during the handling and cutting processes using tweezer and a pair of scissors respectively. However, this substrate wrinkle is not the main reason for the degraded quality of graphene grown on the substrate. Meanwhile, the roughness at the edge area of the cut substrate may be reduced by controlling the speed and the angle of the cutting forces. Finally, the information obtained from this preliminary study on sample preparation is important for future work in the synthesis of graphene nanocomposites for its application in nanofluids. That's all. Thank you very much.